Welcome back. So far we discussed three modes of heat transfer. Let us recollect what we discussed so far. So in the case of conduction heat transfer, we obtained this Fourier law of heat conduction. Fourier law of heat conduction. We obtain expression for rate of conduction heat transfer. Q conduction is equal to minus Ka dt by dx, which can be also written as minus Ka, to be precise, A suffix n, T2 minus T1, final temperature minus initial temperature by L, and this can be conveniently written as Kan, T1 minus T2, minus n can be taken inside, and to obtain the electrical analogy form, you can write T1 minus T2 divided by L by Ka suffix n. So if you want to apply it for assume that there are two walls. As already we discussed, we wrote for this also. Let this be K1, thermal conductivity, K2, let this thickness be L1, let this be L2, and let the area be AN, or simply A. So far we discussed as AN, let us have it as AN. And we can draw a circuit very easily. There are two materials, two resistances. So this surface is at temperature T1, this at the intermediate temperature is T2, and this is T3. So here we can write T1, intermediate is T2, and this is T3. Here we will have L1 by K1 A suffix n, or simply A, L2 by K2 A suffix n. And you can add any number of materials to this. You can have 5, 6, 7, etc., etc. So this is very much useful in analyzing many heat transfer problems. Now let us discuss the convection heat transfer formula. So we remember, for convection heat transfer formula, we obtain Newton's law of cooling. This is written as Q convection is equal to H into surface area into Ts minus T infinity. This also can be written as Ts minus T infinity divided by 1 by H A suffix S. So here we can write like this: Ts T infinity 1 by H into A suffix S. Very simple. And you may have a combined problem like this. Assume that for simplicity I am considering two materials. There are two different layers of solids kept like this with thermal conductivity K1, K2 and L1, L2. Assume that some fluid is there. Some fluid is there which has got the convective heat transfer coefficient as Hi, initial temperature is Ta. And here there is some other fluid. On the other side you have some other fluid which has got H0, T0. Assume that Ti is greater than T0. And here you will have a different temperature which is called as T1. At the interface you will have some lower temperature T2. At the outer surface of the outer solid is T3 and T0. So here you will have convection resistance. I can draw like this: convection resistance. And for this material I have a conduction resistance, first material. For second material I have a conduction resistance. And again I have a convection resistance outside, H0. So this can be written as Ti. So here temperature at the interface between the inner fluid and the inner wall is T1. Here it is T2. Here this is T3, and here it is T0. Therefore this becomes 1 by HA. See, very easy to write. So I can take this area as A. So this area can be taken as A. This is the area normal to heat flow for conduction. This is the surface area for convection. Both are same. So L1 by K1A, this is L2 by K2A plus 1 by H0 A. Very simple. You can write equation as Ti minus T0 divided by, you add all the resistances, 1 by HA plus L1 by K1A plus L2 by K to A plus 1 by H naught A. It is very simple. Q is equal to. And as far as the radiation is concerned, we obtain this equation. Q radiation is equal to epsilon into sigma into surface area into Ts power 4 minus T infinity power 4. And we said this should be in terms of Kelvin. And here generally radiation combines with free convection and conduction. In forced convection ambience, forced convection situations, radiation negligible. So generally a term Q combined is used. Q combined is equal to H combined into surface area into Ts power Ts minus T infinity. This H combined combines both radiation and convection. It combines both radiation and combines both radiation and convection. So this H combined, if you solve, you will get an equation like this. H convection plus H combined epsilon into sigma into Ts plus T infinity into Ts square plus T infinity square. So with this we come to the conclusion for first CO. CO means course outcome. We have discussed the various modes of heat transfer. Let us see in the next class. Thank you.